that, is the audio on or? Do I have the audio or? Okay. Hello, test. 1, 2, 3. Okay.
So are you doing that or am I doing this? If you can do it. Don't have to do the work here. Here's the camera. Punch up. Right now I have scissors.
Oh, look. I don't know if that.
I don't know if he's on the Zoom or
Okay.
This guy here, right? Yes. And I assume Karl will start with talking about what he's going to do and all that. Okay. So this is what we're streaming right now. Yeah. Just his title slide. Okay. So this is what's going out, and this is what's available. Get there. Yeah. Okay.
Yeah, and I probably, when I talk, I'll be next to the computer. And I'll have a few little props and stuff, but.
And that will be can do. Right. Okay, that's easy. Yeah, I mean, yeah. Can we can
And the arts and picture setup, so we could have a slide full screen and take this image and sticks it in the corner. So if we need to see a talking head,
Yeah. So are we going to have like any LAS like business, or are we just going to go straight? I know tomorrow is
push for volunteers for Clean UAC, and tomorrow night's
public.
night, and we're looking for presenters.
Okay.
I got more useless pictures. If I can't see something, I take a picture.
Can we do this? All right, so get in a given frame, and you just punch up the camera. Well, good evening, everyone. Welcome to the LAS General Meeting. Our guest tonight is Karl Schmidt, but before that, I've got a few announcements. Incidentally, I'm Tom Hayes. I'm the webmaster, guy that plugs all this stuff together and tries to make it work. We're looking for a few things. Good news is tomorrow night is a public night at Kirby, and we've gotten a go from Ronnie that everything's going to be wonderful for tomorrow night. Also, our UAC, the Urban Astronomy Center up at Tom Sawyer Park, has turned into a warehouse. We have so many donations of other equipment. We need to comb through it, decide what's good, what can be sold, what we want to keep, and what is just junk that should be tossed so we can find some floor space in the room again. So we're planning on doing it on Wednesday nights, but keep a look on the website and even Facebook, and we will announce it for sure. We're going up there on Wednesday night to try to clean the place up a little bit. Also, for you people who want to do something for the LAS, we are looking for other presenters. Karl is going to do a great job tonight, but we have future meetings. If you have some aspect of astronomy you'd like to talk to everybody about, just contact us, send us an email, and we will get back to you about that. Now, our guest tonight is Karl. Karl Schmidt has been an amateur astronomer for over 40 years, although he doesn't look that old.
No.
But in '91, he joined the LAS and has been involved with all avenues of public outreach. His interest in astronomy began in the early 1980s using a pair of 7 by 35 binoculars to explore the night sky. He has built many telescopes from a 3-inch refractor to a 10-inch Dob. His passion is observing the night sky with his 12.5-inch Star Master, exploring galaxies and galaxy clusters, recording details he sees. He's also passionate about helping others learn the night sky and how to use their telescope. So, Karl, it's all yours.
All right,
Thanks.
thank you. Can everyone hear me okay with the mic? Okay, great. Well, welcome to tonight's meeting. Just a show of hands, who's like new here as far as looking to purchase a scope? Okay, we got one, which is okay. Right. So tonight's presentation is going to just basically go over like a few of the attributes in selecting a telescope. It's more or less for the beginner. There's a lot with astronomy and selecting telescopes, accessories, and so forth, but we're going to be focusing on just the visual aspect of it and how we can use the focal length, the exit pupil, and also the aperture in determining how we choose a telescope. Also, after the meeting, I've got some books and some binoculars and a small scope for just kind of a show and tell for those who are new and like to get a kind of a peek at some of the beginner stuff. Again, tonight, what I'm covering is just say that the foundations of it. There's more to it as far as I won't be covering like filters and Barlows and other accessories, but a lot of the books that I brought go more depth that talk about that help with your journey in pursuing astronomy. Let me on. Oh. Oh, how do you get this clicky? Oh, turn it off by accident. No. Okay, thank you. All right, all else fails, we'll. I think it might be the computer. All right, hang on. All right, I'll just use the. So like I said, visual astronomy is what we'll be concentrating on, choosing our eyes, binoculars, and a telescope to view the night sky. Before choosing your telescope, one of the things you want to do is learn about the night sky. So you want to get a planisphere like we see here. You want to go out and start learning the bright stars, start learning the constellations. So this is a snapshot of our early spring, summer. You can see Polaris, or North Star. You have Ursa Major, which is the Great Bear, but there's an asterism in there, which we're all familiar with, is the Big Dipper. And usually we come up with sayings like the handle of the Big Dipper, you arc to Arcturus, and you spike to Spica. Other constellations, the bright stars, make up the summer triangle. As you can see, Deneb, Vega, and Altair. And then going down south, we have Scorpius. Antares, the bright star, will be one of the constellations that I'll be premiering tonight. In the wintertime, you have the winter hexagon. There's a lot of bright stars. You can see this person here. We'll talk about what they're doing here with their fist. They have their star map book. They're looking at the night sky, learning the constellations. Once you know the bright stars and the constellations, you can move up to looking at your first purchase as a pair of binoculars to get a little closer look. All the equipment that I'll be showing tonight is just, my suggestions. There's a lot, but there's going to be certain aspects that I'll point out when you're purchasing your first pair of binoculars or telescope. Here we have a 7x50 binoculars, and this is a good entry. You don't want to go any greater than 10x50. They get a lot heavier. 10x50 binoculars is heavy enough and comfortable to hold in your hands for viewing the sky. So in the specs of anything that you're looking at, there's a lot of information here, and as we go through the presentation, we'll get into the more detail. But this one here is the Poro Prism, the type of glass. These are the coatings, and you're really looking for fully multi-coated optics, and we'll explain why that's important. This XLT coatings is what Celestron puts on their lenses to help with the transmission of the light rays from the objective down to the eyepiece. Exapupil is important. We'll be talking about that, and we'll know what 6.4, if that's a good exapupil or not. And then the eye relief. One of the important things, in not only with binoculars, but with your eyepieces, especially for me, I have astigmatism in my eye, so I have to wear my eyeglasses, so I want a long eye relief. So I'm looking at eyepieces with like a 14 millimeter or greater. Some of the eyepieces with the starter scopes are less than that, and it's kind of like looking at the little porthole in your door when you're looking outside. It's so small, you got to get your eye directly on it. With the eye relief, you can be comfortable enough away so that way you're not up close and getting that kind of tunnel vision with the eyepiece. So you may own a pair of binoculars. Any pair of binoculars are good. The reason the Poro Prism is of choice is because it provides a wider field of view. It's just the way the configuration of the optics are. But if you own either pair, you're on your way to looking at the night sky. So now that you learned the bright stars, you can identify the constellations. Now we can start looking closer and exploring the constellations. And always pick the Big Dipper and the Little Dipper. One thing is our North Star is good for the telescopes that are an equatorial mount for pointing to the celestial pole, which is roughly in there. The nice thing about these two constellations, you can see them year round. Going a little deeper is the magnitudes of each stars in the Little Dipper. It does several things. One, it gets you familiar from your star maps that we'll be looking at, kind of an idea of how bright a star is and how do you relate that to a star map. Also, it's a good guide for, like in Fern Creek where I live, I can see about 4 of these stars, but if you get out to Kirby on a good clear night, you can see up to 6 or more. Now, looking at the night sky, it's getting a frame of reference of how many degrees of sky you see. The Big Dipper is a great tool for determining degrees of sky that you can see. So in the binocular example, it was a little over 7 degrees, so you could see the pointer stars that point to Polaris will fit nicely within that binocular field of view. This double star down here is 12 arc seconds. There's 60 arc seconds in 1 degree. A lot of people with good vision can split this with their naked eye, but it's also a nice binocular object and also a good one to test the clarity of the sky, which we'll talk about later on as far as seeing in transparency. So remember the observer holding their arm out at length. She was probably trying measure, so your hands can be used as a guide as far as helping you know, how many degrees of sky that you're seeing. So she was probably looking at 10 degrees. The Big Dipper, for example, of 25 degrees, holding your hand that way at arm's length will give you a good reference of how much sky you're seeing. So once you've learned the bright stars and the constellations, you'll get to some more sophisticated maps from the planisphere. This one here, and I've got the Pocket Sky Atlas from Sky and Telescope here tonight. You can get a little more detailed maps. Now Polaris helped us determine the brightness of the stars, and here we have a little guide to kind of tell us from magnitude 1 down to magnitude 6, which is they go from brightness down to the dimmest in the numbers. So anything past 6 is much dim, and our eyes are right around the 6.5 mag is what we can see with the naked eye. But the map, it'll kind of show you the bright stars to help you identify what you're looking at. For example, the square of Pegasus here. We can look at this map and know it's 15 by 15 degrees, and we know that because we can come out here and go from 30 to 20. We know it's 10 degrees, and just about half of that is 5 degrees. So we know that's roughly about 15 degrees. So this is your, what we call the declination coordinates. The coordinates going across here is right ascension, and for every hour of right ascension is roughly 15 degrees. So we can see if we take Alpha Andromeda and Beta Pegasus, if we were to turn it on its side here, it would roughly give you that 15 degrees. So now that you have an idea of the bright stars, knowing the constellation you see, you can start looking for deep sky objects. So in this map here, we have the Andromeda galaxy, and you may have another book that has a little bit more detail on how to find it. One of the methods is star hopping, so you found Alpheratz here, and then you just kind of star hop over to Merak and then go to Andromeda. Or you can start up in Cassiopeia and then take Shidar and kind of point down to Andromeda. So the question here about how many degrees is that star hop there? Well, we know that the square of Pegasus is 15 degrees. So if we go from here to here, that's almost 15 degrees. From here to Merak, anyone want to take a guess? About 10? We'll go with 25 degrees. Well, you're close. But from here to almost the Andromeda galaxy is around 10 to 15 degrees. But as you can see, if you hold your hand at arm's length, this is about the size of the Big Dipper. So again, this is just estimations, and it also helps you in locating deep sky objects on the map. A lot of maps will have like a little field of view for the binocular field of view. It'll state that on the map. Sometimes those are 5 degrees. So we can see from Merak, you're about 10, if this is 5 degrees, about 10 degrees to find M31. So Scorpius is one of the constellations I'm highlighting tonight because June, July, and August is a great time to view this constellation. It's low in the south. It has many, many deep sky objects as far as naked eye, and also as binoculars and telescopes. Out of the 18 recognized stars, 13 of them are brighter than magnitude 3. And one of the neat things about Antares here, it is a variable star. So it varies in magnitude. So here is the names of the brighter stars. And again, we don't have to memorize these, but at least want to be familiar when we do get into a go-to telescope and you have to look at the bright stars on the little keypad to line your scope. One of the stars will be Antares, so at least you know where that is in the night sky now, and you could be able to identify it on the keypad. From here we know this is roughly 50 degrees, so let's just say from here to here is about 25 degrees. So again, you're getting perspective of how much sky you can see. What makes this interesting here is these two stars here. This is mu1 and mu2, and it's a naked eye double. If you can see this low in the sky, then your transparency in seeing is really excellent for tonight. Also, the stinger here with Shula is another one. It's a wider pair that you can see. This little cluster here is M7. It's roughly 1 1/3 degrees of sky. So a lot of the books, like I'll be showing after the program by Sue French, they have a lot of the objects as far as the degrees and arc minute size. So it gives you an idea when you choose your telescope after you're looking at binoculars, you know, what you want to see as far as, you know, a real wide field of view or a real narrow field of view. So in here you'll find open clusters, globular clusters, nebula. There's a famous galaxy in here. Does anyone know that famous galaxy? It's the brightest galaxy in the night sky. The Milky Way, yeah. Yeah, so not a trick question, but we get to see our own Milky Way galaxy. So from the stinger, as you move up, there's a lot of bright, like the Lagoon Nebula here, M22. Like I said, M7, there's another, and M stands for Messier. M4, there's M80. So there's a lot in here that you can see with binoculars and small telescopes. The other constellation I like to point out is Sagittarius. There is another dipper in here that I like to point out. And here's the bow here, and then there's the handle. So for me, it's just another asterism. I like to say someone tipped over the pot and the steam is, you know, rising the Milky Way that we see. So once we're familiar with the sky and we've looked through binoculars, we have kind of a good feeling of what we want to see. Maybe globular clusters is an object. So we start thinking about, you know, what type of telescope, and there's all types of telescopes, all different types of features. There's commercial made, there's do-it-yourself made, there's different like Schmidt Cassegrains, refractors, you know, short tube, long tube. We got a small 6-inch stop here, and then some larger refractors over here. This is the 3-inch refractor Richfield telescope that I built. So there's all types of telescopes, but which telescope is right for you? Well, before we get into answer that, we got to look at some of the things, just the features of the scope between frustration and satisfaction. A lot of beginner scopes, a lot of companies and suppliers will give something of this, and they'll advertise you can put your cell phone or get, you know, great images of the moon and all these accessories. But what's frustrating about this is this tripod here. It's very lightweight aluminum. This equatorial head, over time it's all plastic, so it's going to get loose. You're going to try to point with this small finder scope, and it takes a long time to really understand it. And then you put your phone on it and it just wants to fall over. Plus, if you want to try to get, up, to the zenith of the sky, it's very difficult with this type of tripod. Now, one of the interesting things about this small 4.5-inch Newtonian telescope, a couple of things here. One is you can go to the free public library and check one of these telescopes out, and after the meeting we can discuss that more, and I think Pat Peak has some information on that, so if you're interested. So you don't have to go out and actually purchase. You can actually go and check one of these out, take it home, and get familiar with the night sky. It comes on a nice solid base, has a, I'm not for sure the eyepiece that we have, but usually they're around a 25 millimeter. It gives you a nice field of view, and they have a red dot finder. We'll kind of use this red dot here. We'll use the O and 4, but you can point that to, like, say, a star, get really close, and then just kind of navigate the scope a little bit, which is real easy to use on this alt-azimuth mount. It's kind of up and down, and this goes left and right. But before we get in, let's get a little bit some units and nomenclature of the telescope. So what I like to do, everyone's familiar with a quarter. It's roughly 25 millimeters. So 25 millimeters is 1 inch. So we can start, when you look at a telescope, they're usually going from 6 inches or 150 millimeters, so it goes back and forth. But if you always think of a quarter and do the division, it'll actually help you if it's listed in millimeters or inches, what you're working with. Also, I like to use the idea of a quarter is because the bigger the telescope, the more quarters, the more price of the telescope. So it's another way to kind of help with the price. In this example here, 100 millimeters is 4 inches. The focal length here is a really long focal length, 1,200 millimeters. So if we convert that in inches, it's 48 inches. And we all know a yardstick is 36 inches, or roughly, if I remember, 914 millimeters. So I'll be using this throughout. This is kind of handy when you're selecting your telescope for several reasons. One is the layout where you're going to put it in your house. And also it gives a good reference as far as length of the tube or your telescope for getting it in and out of your car or whatever vehicle you're transporting, or even in and out of your home. So this is a good guideline here. 700 millimeters is 28 inches, so it's a little less than the yardstick. And then if you take, which we'll see when we get into the formulas here, this 1,200 millimeters, and then we divide the focal length by the aperture, that's going to give us our focal ratio. And we'll see how that comes into play and why that's easier to think sometimes as a ratio than the actual millimeters. So the attributes to selecting your telescope, we're going to first think about focal length. Again, going back to the yardstick, is you're transporting it. If your scope's like really, really long, how we're going to get that through our door of our house, how we're going to get it in our car. Also, the focal length is going to determine the field of view as we see, how much sky we're going to see. We're going to talk about exit pupil, and that's going to be a function of magnification, but I like use exit pupil because we're going to talk about our eye. When we get dark adaptive, for most of us, our pupil is going to dilate up to about 6 millimeters. It's going to vary with age. Some of the younger adults can go to 7 millimeters. A lot of the older adults maybe get down to 5 millimeters. So that's going to vary, and we'll see in selecting eyepieces why that's important. What everyone talks about when choosing a scope is aperture, and aperture is, I say it's the least. For one, it is important, but it's not for one, like I said, as you go larger in aperture, the more price in the telescope. The aperture is more of just the light gathering power we see is how you look at an object to discern detail as far as, splitting double stars, or if you're looking at, say, a globular cluster, the one of the examples, seeing, the clarity. So when we get to that slide, it'll make more sense. Some of the terms we've kind of mentioned is focal length. When we're talking 750, or depending on the aperture, but we'll just say here f5, so that's going to give you a wide field of view. So the smaller that number, or the small ratio, is what we call a rich field telescope. The longer focal lengths is the narrow field, the more magnified the field of view is going to be with the eyepiece that you use. Magnification is a function of the focal length in the eyepiece, and also you can calculate the exit pupil. And then the aperture, we're just using a refractor here, but that's your lens or mirror, the size of your instrument. So just looking at the formulas, and I'll explain them as we go, but one of the things I want to point out is on the telescope, sometimes there is a nameplate that gives the aperture in millimeters and also the focal length. So using these formulas here, we can calculate the F ratio of a telescope. We can also calculate the exit pupil and also the magnification. So if you know the telescope's focal length and the aperture, you can find the focal ratio. The aperture of the telescope divided by the magnification will give you the exit pupil. And we'll see how all that works here in the upcoming slides. This telescope here, again, if you take your yardstick, and this here is an 8-inch, I'm not for sure of the focal length, but let's just say it's an f6. So you can take the 6 times 8, which is 48 inches, so you know it's going to be a little bit longer than the yardstick here. And if you place this yardstick, in front of your scope, of course this scope will be sitting upright, but one of the things is storing it. You can figure out like how much space you need in a spare bedroom or basement, so that's why the yardstick comes in handy. It helps you determine the size and also the focal length of the telescope. Also your eyepiece case and other accessories and storing those. So there's many different types of telescopes. We got refracting, reflecting, and then the catadioptic, which there's a lot of different flavors there. Most of them are Schmidt Cassegrains and Max-Sutov Cassegrains. This diagram just shows the light path. There's your aperture here, which is a lens, your aperture here, which is a mirror, and then your aperture here, which is a mirror, but this is a combination of a mirror and a correcting plate, which is a lens, with another secondary. So this is what sometimes refer as a compound telescope. So all these have different form, fit, and function, but it's all based on the focal length. So let's start with the refracting telescope. It usually has a lens up front. There's no obstruction into the light path. It comes back to the cone, comes to a point. That's where your image, and that's where your eyepiece examines the image. These are just examples. I would say kind of the medium range, not the advanced that we'll talk about here, but good starter scopes. If you remember in one of the earlier pictures, here's the 102 millimeter Celestron, and you can see here it's 1,000 millimeter in focal length, and it's an f9.8. So looking at that, we know that's a narrow field of view. Over here, this same aperture, but a different focal length, we're at f6.5. We know that's going to be a wide field of view because the focal ratio is small. So depending on the eyepieces that you put in these, we'll see that the same 25 millimeter eyepiece will give you different results in both of these telescopes, and it's all of the function of the focal length. Also, thinking of portability, again, this telescope here, going back to the yardstick, is really long. So if you think about putting it in your car or where you're going to store it, it's long, where a short rich field telescope is much easier to transport or store. So we talked a little bit about with the binoculars and the coatings, and we want to get a little bit more into that with the telescopes. It's important when you're looking, when you're choosing your telescope, is read the specs, because it's going to have critical information to help you what type of lens or mirror. Here we can see coated, multi-coated, but what we're looking for is that fully multi-coated. What it means is both sides of all the lenses in the telescope, as well as the eyepieces, give you the most transmission of the light to pass through that substrate. With no coatings in this diagram, we can see there's a lot of light that bounces back, so it's not getting to our eye. As you get more and more coatings, the better the light transmission, but also the better image you're going to get from that telescope. Here we look at just normal glass. The light doesn't come to exact point, so you have some color aberration. There's different types of glass combinations that's known as ED glass that gets that color more pinpointed to a closer focal point where you don't have the color aberration. So what that ED stands for is extra low dispersion, and we can see in a single lens all the different wavelengths of light are not coming to an exact point. So I use the moon as an example here because it's the easiest to see. In this image here, we can see that like little color halo, and that's chromatic aberration. When we're using different types of glass, and then with the coatings, and even if both of these had the same coatings, which most of your lower quality telescopes won't have the fully multi-coated, but the different types of glass, you're going to get all the rays of lights to a common focus, and you can see that you get a much clearer picture or image of the moon. So here's some comparisons of different types of refractors. And you can see this one over here, this one with the ED glass, you get a real sharp, crisp image of the moon. As you're going over to other different types of refractors, you can start seeing a little color fringe. You won't notice this much, say, on the deep sky objects. You'll notice it definitely on the planets, and especially the moon. So a lot of times you really want to look at the specs and see what type of coatings and glass before you actually purchase a refractor telescope. But there's also another type of refractor. It's the apochromatic, and it's the one that's really corrected. And when they go short by apo, and how I kind of like to remember this, the apochromatics is the P, all the different colors of light come to a point. Also, the P stands for price. They're very pricey, but they're excellent telescopes. The achromatic lens, you have the C there for color. You're going to get that color aberration, and the cost isn't as much. So the C stands for cost, lower cost. So, and you'll see when you're looking at telescopes, you see the achromatic refractors, you're going to see the price almost 3 times jump from the ED type refractor lenses. One of the telescopes that I'll recommend for beginners, and again, I don't know all the prices, and a lot of times during the holidays, different manufacturers and suppliers will have them on sale, but this one here is an Explorer scientific telescope. We can see it's an f8, so it's about that mid-range. It's not a real wide field, it's not a real narrow field, but it gives you kind of a medium field of view. It's an 80 millimeter, which is right around 3 inches. It comes on this really sturdy alt-azimuth mount. It has the, the up and down. I think this one, or that one there is the lock for the telescope itself. This is for the up and down lock, and I think this just swivels here. So it's the alt-azimuth type mount, which is real easy to use. It's just point and observe. We notice here it's got 2 elements. It's a doublet, but it doesn't say what type of coatings. But knowing it's a doublet and it also states that it's fully multi-coated, you know you're getting a quality refractor. Now onto the telescopes I'm familiar with and I like, and everyone has their own choice, and there's no one telescope that's better than the other. It's the telescope that you pick and that you get the most use out of is the best telescope for you. The reflecting telescope, which is the Newtonian telescope, has a primary mirror, and then it has a secondary mirror that takes that light cone and puts the focus right at the edge of the focuser. So in these telescopes, the real short focal ratio is a real rich field of view, and then the long focal ratios are as the narrow field of views. The price on these, depending on how much glass they have to grind to get to the focal length, will determine the price. So as they have to grind more to get it deeper, a lot of times the price will be a little higher for the wide fields than the narrow fields. So some of the attributes to look at with the Newtonian telescope, they come with different types of glass. The one that I always recommend is the Pyrex, because it has, the glass is much more hardiness, low thermal expansion as far as cooling. You want to look at the coating around 93% reflectivity. They do go down to 89%. So the reflectivity is just more of the transmission of the light getting to the eyepiece, and it's usually aluminum with a silicone dioxide coating to help protect that aluminum coating. A lot of the questions you get, what's the best telescope? And again, that answer is the telescope you use the most. But if you're looking at price, getting a good quality telescope is going to range from $3,000 to around $1,500 to get into a good quality scope. The prices can go higher depending on the type of glass. But Apertura has a 8-inch Dobsonian, which I'm kind of partial to because the features that it comes with, and one of our members, Bill, owns a 12-inch that I got to view through, which is I find a great telescope. You can't beat it. I think this one here is roughly, don't quote me on this, like around $800, $850. But what it comes with is these features here. So a lot of your beginner, intermediate, gives you eyepieces that are not of good quality, but here they give you the best of both. They give you that 9 millimeter with a 52-degree field of view for like looking at planets or high details of the moon or even splitting double stars, but they also give you a 30 millimeter 68-degree wide eye field eyepiece. The focuser will take 1.25 inches and 2-inch eyepieces, which is nice. It comes with an 8x50 right angle correct finder. I really like that because when you look at your star map, most of the finder scopes that come on your entry level, everything is upside down left to right, so it's kind of hard to use your star maps. But having a correct image right off the bat is something that you don't have to purchase as an extra accessory. The focuser is a dual speed, what's nice about that, the larger knob is more of a macro focus, and then that little knob here on the end is more of a micro focus. So that's a very nice touch, is getting that image that you're viewing into focus. So we can see here in the specs on the supplier's website, there's the aluminum silicon dioxide mirror. Will come down. They also give you as far as weights, which is important. Most of us, not all, lifting something heavy, we got to think about our backs, especially as we get older. So this one here is, in my opinion, is not that heavy. Again, we're looking, I think it's maybe the next, or maybe the previous slide. Yeah, F6. So that's 1,200 millimeters. So it's about almost a yardstick and a half. So it kind of gives you an idea of the size as far as what you're picking up. And that smaller 8-inch F6 that we saw had a handle on the back, so you can actually put a hand underneath the tube and a handle and pick up. So again, if someone asked me what's a telescope I would choose, if the money was say not an option, but $800 you can get you a nice telescope that has a lot of light collecting power. It's good for planetary and also deep sky objects. So that F6 again is kind of in the middle range of both worlds. Now I haven't mentioned anything about the Barlow lens, but I'll mention it now. The Barlow, like a 2x Barlow, all it's doing is doubling the focal length. So if you want it to get more magnification on a night that's exceptional as far as looking at lunar detail or splitting stars, this telescope will again be equivalent to almost like an F12. So the catadioptic telescopes, as we mentioned, has a primary mirror, a secondary mirror with a correcting plate, and it's a folded light path. And they have a Cassegrain and a Max-Suthoff, and I have a little Max-Suthoff over here on the table, which is 90 millimeters, and it's, if I remember, it's F13, but it's written on the nameplate. We'll look at it. But again, if we would take that mirror, it would be longer than the yardstick. So again, this is a real compact scope. It's a grab and go scope. So that's one of the things with the catadioptics. It's a compact scope, but they also are a little expensive. And the reason why they're expensive is because, again, just how they are manufactured and made. It's a lot of optical, getting everything aligned and corrected. A good starter scope, again, if I had to throw a price out there for us who are interested in buying, is around $1,500 for this. And just to clarify, I have nothing to do with this telescope, even though it has my name. So again, here's the specs of it. It's an F10. So you can put a Barlow in it, double it, and go to F20. They also have a focal reducer, which we won't talk much about, but it's also to change that F10 to make it a wide field, which a screw on the back of where the eyepiece diagonal goes. So again, you can transform these scopes into a real narrow field or wide field by adding additional accessories. Again, we can see Celestron. They have their special Star Bright XLT coatings. Again, I don't know what all that is, but it does help in viewing the older Celestrons and the newer ones. You can see a little difference. So the coatings are making a difference with the light getting back to the eyepiece. Special feature of this, it's a go-to. For me, I'm really old school. I star hop. None of my equipment has any electronics on it. But again, there's no downside. If you know the night sky, like I mentioned earlier, if you know the bright stars, this equatorial wedge, they do come with a little polar finder scope. Once you get close enough to the Earth's rotation with this, and then you plug in the information, a couple bright stars, it's a good go-to. If you get an eyepiece about a 1 degree field of view, usually within rough polar alignment, you know your object would be near the center, and then you can use the keypads to center it up. The tripod is very heavy and sturdy. It's not the flimsy, you know, aluminum plastic types we see with the entry-level telescopes. But going in with the Maksutovs, these here are about half the price. Again, we're looking on the specs here. It's an f14, yeah, 100 millimeters, so it's almost a 4-inch aperture, which is going to be a similar size here on the table. It doesn't mention anything on the coatings or the optics, but talking to the supplier or more getting into this one here is Explorer Scientific, so I think it's High Point Scientific. You can always call them up and get a little more information. This is a good equatorial heavy-duty mount. It's got slow motion knobs, so again, it's kind of a point and shoot, and when you get close, you can use the knobs. It's kind of a macro adjustment to get the object in the center of the field of view. So there's a lot of different finder scopes. Again, I mentioned the correct image. I'm partial to that. It really helps with the star maps. The two out there on the market are 8x50 and a 9x50 by Orion. Both are great. There are many different types of red dot. I'm partial to the Tellerad because it has a 0.5 degree, 2 degree, and 4 degree circle. So again, that helps you when you're star hopping or navigating, because you already know from learning the sky, like how many degrees between the stars is. So this gives you a good icon in the sky to actually point and navigate your telescope. So we saw a lot of different types of mounts. We got the Alt-Az, which is just the left and right and the up and down. The Dobsonian, which is similar to like a Alt-Az mount. And then we have this equatorial mount that points to the Earth's rotational axis, which is close to Polaris. In this image here, these mounts, they have like this little U or whatever. Stay away from those with the longer tubes, because a little wind out will start vibrating the scope, and it causes that frustration when you're trying to view an object. But the Dobsonian mount, and then these equatorial mounts that are nice and heavy, and let's look at some examples here. The tripods that are real, what I call beefy, are going to give you good, stable views with your scope and not much vibration. There's also some one-arm Alt-Az mounts that have a heavier tripod. They're real nice for little refractor telescopes. And again, the Dobsonian is just a box and with a bearing here and a saddle that holds the tube to get the up and down and the right and left motion. One of our members, they have this, it's a different brand, but it's similar to the Skywatcher's AZ5 mount. Again, it's an Alt-Az mount. If you're looking at just a push and go and you want something of a rich field telescope and not all the trouble with setting up an equatorial mount, this may be an option for you. So not only the focal length, but also the type of mount is real critical because you want a good stable mount. So now let's talk about our eyes. And again, I'm no optometrist, but what I do know is that everyone's eyes are different. Some of us don't need to wear glasses. Some of us do. If you do have astigmatism like me, you're going to need to wear your eyeglasses when you're looking through an eyepiece. Without it, everything looks blurry. For us young folks, we have a young person here in the audience. Your pupils are really going to dilate because you're younger. Us older folks like me may not get that aperture opening. And what we're talking about is your pupil in your eye. So as you get dark adapted, your pupil is going to expand. And there's a chemical in your eye that helps your rods, which is rhodopsin. And it really helps with the night vision. It takes roughly 30 to 40 minutes to get you fully dark adapted. And where your cones stop, they don't stop working, but it's where your rods take over so you can visually see in low light. But if someone takes out their cell phone or a white light, then like that, your night vision is gone. Then you have to wait another 30 to 40 minutes to gain it back. It's one of the reasons why we use red light, because the red light has a higher wavelength. I think it's 700 nanometers in the red, and our eyes dark adapted is around the green-blue, around 550 nanometers. So the red light is not going to affect us as the lower wavelengths of light that are bright that cause the iris to close. So this exit pupil is really important because that cone of light coming from the telescope is going to enter your eye. And we're going to see here in a moment how that works. But I want to go back because in one of the equations we talked about the aperture and the magnification, but the other piece for exit pupil, you could take the eyepiece focal length, which is printed on the eyepiece, and divide it by the F ratio and get your exit pupil. So let's take a look at that. So in your telescope, we have from the primary or aperture to light that comes down to a point, and then your eyepiece inserted to see that point. And that point is really the image that is made. Your eyepiece is the same as a telescope. You want the fully multi coatings, good quality eyepieces. All this inside here is really black and dark. Even a lot of the lenses on the edge are painted to, you want no stray light getting in to affect your image. We talked about eye relief, the distance your eye from the eyepiece. For me, I like a longer eye relief. But as the focus comes in and goes through the elements of the eyepiece, it's going to produce like a cone. Think of it as like a little ray of light that's going to enter your exit pupil. So the size of your exit pupil is important depending on the type of eyepiece. So for the example here, I took an f8 and an f5, and I've chosen a 40 millimeter, 25, and a 10 millimeter. So the eyepiece focal length here, you're going to divide it by the ratio of the telescope. So let's look at the f8 and f5 here. So that cone of light coming out, we see that in a longer focal length with a 40 millimeter is going to produce a 5 millimeter cone of light. Well, that's really important because that's all that light's going to go into your eye. But if we go in a much faster telescope, that 40 millimeter is an 8 millimeter exit pupil. So we're going to have a little loss of light. Not all of it's going to go in the pupil of our eye. If we get down to say a 25 millimeter eyepiece, we can start to see as we decrease, the exit pupil decreases, but also depending on the focal length of your telescope, it's going to change. So usually the sweet spot for me is between 3.5 to 5 as far as like the cone of light coming into your eye, depending on the scope you use with the focal length, how bright the object is in relation to the focal length. And on excellent nights, if you get with your 10 millimeter, same calculation, you can see that even drops smaller. So eyepieces come in all varieties. Again, we go back to that little peephole in your door where you had to like get your eye up really close. A lot of the beginner telescopes, they advertise as a 26 millimeter. Here we can see the glass here, but those beginner scopes, they're 25 millimeters, just like a little peephole, like looking through a door. But these here are kind of your mid-range, so the distance across here is what's determining the size of the eyepiece. Again, there's different types of field of views. This here is the 68 degree. I think it's Explorer. Yeah, scientific, and it's got fully multi-coated. My eyes are bad, I gotta get close. Yeah, fully multi-coated. Again, I like the 68 degree. Most beginner or plossos are about a 52, 55 degree. And we'll show what that is here in the next upcoming slides. But there's different types, Explorer Scientific, the Teleview, Panoptics, even the Orion Q70, which is not made anymore. All these are kind of your medium level with Teleview. Again, it's a discussion, but they're considered one of the high-end types of eyepieces. But all these are good equivalents, eyepieces from your telescope as upgrades. But let's talk about that focal length and what's going on here. And again, when you're looking through the eyepiece, think of that, again, I keep going back to the door analogy. You got your little peephole, then you have your standard window, and then you have your bay window. So the focal length of your telescope is going to determine like the size of the sky, how many degrees you're going to see. So if we look at, excuse me, this chart here, your image magnification for a wide field, as you see here, you have the Pleiades star cluster, which is a real wide field. The Pleiades, if I remember, is 2 or 3 degrees across. But again, it's a real wide field, and when you put in a higher eyepiece, you still have a real wide field of view. A longer focal length telescope, f10, it's a much narrower field of view. And you can see here is when you magnify, if you notice this little triangle here, it's that triangle right there and right there. So this kind of gives you the difference in the focal length of looking at an object, of how you're going to see the object, with a particular eyepiece. And again, M45 is a nice binocular object. So, you may be considering, well, I want a telescope to get a little bit more magnification view of it, but I don't want to lose the cluster itself. So this is where you may want to look at a refractor or a reflector with a short focal length. Or if you're interested in more detail, getting into double stars or planetary nebula, you may want to go to the higher focal lengths to get a little more magnification, zoomed in to see detail. And keeping with that, the eyepiece, we talked about the 50, the 60, the 82. It's marked as the apparent field of view on the eyepiece. So again, that window, as you're looking through, that smaller number on there is going to tell you how, if you're looking through your window or your bay window with your telescope. So as the telescope, um, like the Panoptics or the Naglers, they're getting up to 68 to 82 degrees. And what's the 100-degree Naglers called? Ethos, yeah. Yeah. So the Ethos gets up to 100 degrees. They're nice for the bigger, 20-inch Dobbs, but for the smaller stuff, I find it, as you pan across, it's almost like your sky is wavy. But for me, the 68 degree I like because when I look at an object, I like having a little bit of sky around, but also your point of interest is always going to be the center of the eyepiece. So let's go back to the refractor. You can do it for refractor or reflector. Let's look at some calculations. So again, the magnification is the focal length of the telescope divided by the focal length of the eyepiece. So we're just using a 25 millimeter eyepiece with a 70-degree apparent field of view. So with the longer focal length, you have 40 magnification. Shorter focal length, you have a lower magnification. So when we put these numbers into the formula, with the longer focal length, we're getting around a little over 1.5 degrees with a 2.5 millimeter exit pupil, which is nice. But that real shorter focal length, you actually almost gain about a degree of sky, and your exit pupil is a little bit bigger. So as the previous slides I showed, that light cone coming from the telescope, the bigger the exit pupil, the brighter your field of view. Now looking at the same object in both these scopes, you will be able to tell the difference, as far as the field of view of size, but brightness is kind of, both objects will appear similarly bright, but one will the shorter focal length to some people will appear a little brighter. So now we get into aperture. So aperture is just going to basically determine how much light. So if you could take like a glass and then say a 5-gallon bucket and it's raining out, that glass is going to collect so much water, and then the bucket's going to collect a lot more water. So the area of your aperture is going to determine how much light you can collect and how much resolution. So this is just kind of an example here. As you increase in a 90 millimeter, which is the scope I brought up to that 8-inch we looked at earlier, in a smaller telescope, you still see the stars around this globular cluster, but some of them, because they're so close, you're not getting the separation of the stars. They still kind of look like they're touching one another, but as you go up in size, they start to separate and become like pinpoints. So as you increase your aperture, you're going to get more, clarity, more in quotes brightness of an object. But it's your focal length that's going to determine as well, play into this here. One of the things I want to point out, which we're going to talk about, this is the perfect case scenario when the skies are perfect, because we have transparency and seeing we're going to talk about that really wipes all this off the map. It doesn't matter if you have a 98-inch or a 20-inch. If your transparency is not good or you're seeing, you're not going to get good views of the night sky. Going into that light gathering power, just another thing. It's not just taking doubling, say if you go from a 6 to a 12, but it's actually you're quadrupling the light gathering power. So it's the area of the mirror or lens. that's going to determine the light gathering power. And again, here we can see smaller aperture, this is going to collect a lot more light with the larger aperture. So kind of in a summary here, the focal length, just think of it as wide or narrow field of view through your eyepiece. The magnification is going to depend on your eyepiece and exit pupil, so that telescope, the image, you're just going to further magnify that point of light. And it's also going to, the different eyepieces and the apparent field of view is going to determine your field of view that you're going to experience through your telescope. And then the aperture is how much light you're going to collect, and larger aperture, the more increased detail you could see. So now we're getting to the using your telescope, and there's a lot of things: clouds, light pollution, travel, even being tired. And then the Newtonians, one downfall is versus refractors. Now the catadioptics do occasionally need collimating, but they don't get out of collimation as much as the Newtonian. But once you learn that, it's nothing difficult. So the atmosphere, it doesn't matter if you have a apochromatic or a nice Dob or refractor. If there's a lot of moisture in the atmosphere, it's wavy. If you're looking over a house, heat in the atmosphere, doesn't matter what quality of telescope you have, your images are going to look blurry. Again, finding a dark site, traveling, or even in Fern Creek, when you do have exceptional nights, you're going to get, skies when you're looking at the moon or the planets, some nice crisp detail. And that's where that dual focuser comes into getting in that micro focuser. You can concentrate on Saturn's rings, seeing the Cassini division. And when the seeing is really good, you get real nice crisp images. And you'll be able to tell because the stars in your telescope, for those who observe, they'll be bouncing around, look like they're on fire, but as the sky gets better and better seeing, the more subtle it is. And you can also see that with your naked eye too. If you look up, a lot of people always say, I see the twinkling stars. But on nights when the seeing is good, it's almost like they're still. So the other thing is seeing. Think of seeing. I like to use the car window as an example. So if you have a lot of moisture, a lot of dew in the atmosphere, it's just kind of like the rain coming down in your car. You're not going to be able to see out. So that's your seeing. And also the heat, the waviness. Again, the window, if you're looking out, if you're familiar with the old houses with the radiant heaters and you see the heat coming off the window. So it makes a lot of shimmering in the atmosphere. The transparency is actually how clean the night sky is. Smoke from forest fires, pollution from nearby cities. So using the car analogy, you can look at your window. If it's real dusty and dirty when you're looking out, you don't see very clear. So there are, in today's world, I don't have to look at the Courier Journal anymore and look at maps and predict, but we have astrophotography is just one. It gives you a 3-day window. Of course, we all know if it's white, it's cloudy. Dark blue, it's clear. They do have on here your transparency. The darker blue, the more transparent the skies are. And this is your seeing here. The darker the blue, the better. More stable the sky is, and again the lighter blues, the more flickering the turbulence in the atmosphere. And then we have the Bortle scale, which is important, and it goes from 1 to 9. And 9 is going to be like near your cities. You're going to have this gray glow from all the lights. in your cities, but when you get out into some darker areas, away from all these city lights, and the sky, the clarity is going to change. And here we see Orion's Nebula. It starts to pop out and be brighter. Also, the contrast through your telescope in near the city and suburbs is not going to be as noticeable with objects, but the contrast here, a lot of your deep sky objects are going to start to pop because you're not in competition with the light pollution. So I think Kirby is around a Bortle 3. So it's kind of hard to bring that here, but in this slide, you see a lot of images, a real colorful Milky Way, but if you're out at Kirby, this is kind of what the Milky Way is going to look like. So if you're talking about seeing and also focusing, this slide here of the moon will kind of help you. So on the left or right, which image is clear, has more detail? The left. That's correct. So how we can determine that, we can look at the craters here, and we'll concentrate on this crater here. And if anyone knows, I took this picture, but I forgot where it was on the moon, and I was trying to find it. But irregardless of that, if you look right there, you see like a little crater on this floor of this crater, but it's non-existent over here. You start seeing detail in the walls of the crater here, which is blurry over here. Much more crisp here than it is over here. You see a little bit of lunar detail. But if you look around, even this little ridge here is much more detailed, soft here. So the image here was because this is here is the seeing, so the waviness that you're going to get. But also, if your focus, if you're not good focus, your image will look soft as well. So there's this here is kind of explaining both, functions as far as the sky and also focusing your telescope. So the moon is really good, a good object to look at that. And I have a lunar map that we can look at. So when you're looking, at a crater in detail, you can see if it's your focus or it's the sky. We didn't talk much about the combination in a Newtonian reflector, but if it's not culminated properly, the image of like Saturn or the moon here, it's going to appear soft in the view. And that's something more, depending on which telescope you get. In the books I have up here, it gets a little more advanced in those topics. So depending on your location, this is my backyard. We have trees, but I do have where it opens up here. We have the neighbor lights. You can use a tarp to kind of block those lights. Have it on both sides. If you travel out to a dark site, you have more open skies, a lot darker to see. Here's two different types of telescopes, my 12.5 truss Dob, and then here's a Schmidt Cassegrain. I got mine set up. It has nothing to do with speed or whatever, but once I have mine set up, it takes a little time with the equatorial mounts, but it doesn't mean that any difference as far as quality of the telescope. But the point of it here is you want to learn your scope, set it up, tear it down at home before you take it to a really dark site to get it set up properly. And the other thing I like to point out, the tarps here, in case you drop an eyepiece case or a screw or something, it's easier to find than trying to hunt in thousands of blades of grass to find a small screw or a cap. Storage and portability. Again, if your scope is too long, will it be able to get in your car? If you have a truck or a van, that's a little different. A lot of people want to store their telescope maybe in a garage or a shed. I don't really recommend that. I like to keep it in a house, in a bedroom, or in a basement. I do know observatories house scopes outside, but over time, if you do keep it in your garage or a shed, not only the optics, but the wood and the tube, depending if it's cardboard or aluminum tube, it'll start to degrade. And also you have other little creatures who like to make homes out of your telescope. So these are just some of the things to think about. Again, we talked about learning the night sky, setting up and tearing down your telescope, planning ahead, making a list of objects, make a light shield. The other thing, I have a black pillowcase that I use to put over my head, either at home or when I'm out at Kirby, just to block as much light, but also once my eyes are fully dark adapted, just to kind of help my eye get that most of the light cone coming out in any of the distance, or if someone does pull out a phone or a bright light, it won't affect me. If you're in the suburbs, usually after 12 midnight, the skies settle down, so it might be a good time to set your scope out, and after midnight is when you do get the best views. And a lot of your neighbors, like my neighbors, his lights go out at 12 because they're on a motion sensor, so that's a plus. Plus, I know him as well, so if it's an excellent night, I just give him a text and he just shuts them all off. So storage and portability, knowing where you're going to put your scope is key, because if you don't have a place to store it and it's bulky getting it in and out of your house or in and out of your vehicle, you're not going to use that telescope very much. And then once you select your set of eyepieces, just make a little note card to have. Jot down some notes on for your star map. You'll see in my pocket sky atlas, I have a lot of little circles and stuff that represent my finder scope for when I star hop. So it's not the telescope or the price of your equipment or anything. It's the person behind the eyepiece that's more important. And for me, it's a lot to kind of condense and go over. There's so much more, as far as usage, other ways to use your telescope. Some of them is measuring double stars. Actually, the variable stars, measuring the brightness with that, not only with the naked eye, but with cameras, and also astrophotography we didn't cover. But just to get into visual astronomy, this is kind of the foundations, and I hope this here helps for those who are getting into astronomy to at least look at the telescopes a little differently, looking at the focal length, looking at the exit pupil, and then considering what size aperture they want. So I'll open the floor for questions, and afterwards feel free to come up. There's some books and stuff, and I'll talk about those after the questions. So yeah. So I know we have one new person that's looking. Just your reaction, was this helpful? Okay.
Yeah, I've been a photographer for a long time.
Okay.
And I'm retired now. I thought I'd like to try. I've always wanted to take pictures of the night sky as well as the day sky. I've experimented a little bit with solar photography, and now I'm
Excellent.
looked up you guys on the internet and thought, I'd try and overcome my natural tendency to be an introvert and take some night sky. I've got some of my photography gear mounted on an equatorial mount.
Okay.
I started off with a fairly good mount, a Star Watcher EQ AL55i with
Okay.
20 pound or 20 kilo, 20 pound.
Mm-hmm.
So I've just finally got it set up. I haven't even taken it out
Yeah.
of the house yet. So, but I wanted to come see what you guys were, just to touch base, see what
Right.
you guys are doing. But this has been very helpful because I will eventually want a good scope. And
Right.
The points you touched on were very helpful.
Yeah. And a lot of these, and I'm no expert in astrophotography, I mean from the day with film, spending long hours just on a guide scope. I'm still learning, with CCD and the ZWO cameras. I do know the light cone coming from the telescope and matching up with the array of the camera, all that similar concepts. Again, wide field and a narrow field, all that comes into play, with astrophotography. Plus, there's a lot of great members who beginner, intermediate, and advanced here with the Louisville Club. So you're at the right place with questions and getting further, in your pursuit. So.
Well, thanks. I appreciate it. And
Yeah.
if I'm totally honest, what scares me the most is processing the data after I've taken the photographs.
Yes, that's a lot of tricky. I'm still learning serial, and it's a lot. I'm trying to get my workflow, and even getting that raw data is a challenge. Luckily, Bill, who's a member here, he kind of seen at home my crude setup and how I star hop, and then how I use imaging, and I don't use an auto guider. I actually use the camera itself and what I call lucky imaging, taking a lot of short exposures, but watching the field of view and tracking, and how I set up my, I have an older Orion Sky Atlas mount, so I do the drift align method. So I spend a little time, looking at a star and correcting my equatorial head to get almost precision polar alignment. So it's a lot to learn.
Oh, yeah.
Yeah. Other questions, comments? Do we have any YouTuber questions or? Well, thank you all. Again, feel free to come up. I've got some books and other little things to go over. For those who are not here, I don't know if you get this on here, but Sue French has a good book on deep sky wonders. Pick it up. Half-price book, Barnes and Nobles, but her description and stuff of objects through various telescopes is, I can read it every night. It's just really amazing how she goes over and describes her methods and star hopping. It has pictures and maps, black and white drawings. Really good resource. A couple books, and it doesn't matter if they're older or not. If you're looking into more information on eyepieces and stuff, Starware is a really good book. And then also the Backyard Astronomer's Guide is another great resource that covers all aspects of telescopes. Both books cover all aspects of different telescopes, eyepieces, Barlow's. One thing we didn't talk about is filters and how filters work. So great resources there. And then for us really advanced hardcore, people like me that like to pick out these, 13th and 14th magnitude objects. Springer has a great series. They cover the moon, the planets, even faint objects, even just like nebula, globular clusters. They're great observing guides. They got a lot of history, especially all the different types of catalogs that are out there. Also, another great resource is the Astronomical League. There's all kinds of programs and certificates and stuff to help you get in, whether it's lunar, deep sky, the Messier, the Herschel. They do have imaging, so it's something to look at, and they have a lot of information, on those types of interest. So, well, again, I thank you all, and